Accelerating fault-tolerant quantum computing with Oxford Ionics and Iceberg Quantum. Ready for a revolution in computing? The race toward fault-tolerant quantum computers, a technology that promises to transform everything from cryptography to medicine, is heating up. But here's where it gets controversial. While some believe practical quantum computing is decades away, others say breakthroughs are just around the corner. So who's really leading the charge? Enter Oxford Ionics and Iceberg Quantum, two trailblazing companies joining forces to make fault-tolerant quantum systems a reality much sooner than many expect. Oxford Ionics, known for their innovative quantum hardware solutions, is now collaborating with Iceberg Quantum, a pioneer in quantum low-density parity-check, qLDPC codes, a sophisticated form of error correction crucial for reliable quantum computing. In simple terms, think of qLDPC codes as the immune system for quantum computers, catching and fixing errors before they spiral out of control. This partnership is set to merge Oxford Ionics' cutting-edge quantum architecture with Iceberg Quantum's expertise in error correction, potentially cracking one of the biggest challenges in the industry. Want to stay ahead of the curve? When you register for free, you join a vibrant network of over 12,000 professionals, including scientists, engineers, and IT experts, who are already shaping the next generation of technological innovation. Your membership includes exclusive insights into the latest developments in high-performance computing, HPC, artificial intelligence, AI, laboratory informatics, and data management. Content thoughtfully curated for professionals in life sciences, academia, and engineering, ensuring you get information relevant to your field. Real-world computing breakthrough stories that show how theory becomes transformative results. Complimentary expert reports and panels, including comprehensive guides like the Lab Informatics Guide. Access to white papers and software updates designed to make your research smarter and more impactful. Take action, sign up today and gain an information edge in this rapidly evolving space. Already a member? Simply log in for full access. Your personal information is always protected in line with our strict privacy policy. And this is the part most people miss. Not everyone agrees that qLDPC codes are the final answer to fault tolerance. Could other methods be just as effective or even better? Do you think this partnership is the breakthrough quantum computing needs? Or is it just another incremental step? We want to hear your takes in the comments below. Designing fault-tolerant quantum architecture. Oxford Ionics and Iceberg Quantum Partnership. Quantum computing is on the brink of a revolution, but one of its biggest challenges remains: how to build systems that can reliably correct errors without requiring an impractical number of qubits. This is exactly the problem Oxford Ionics and Iceberg Quantum are tackling head-on with their new partnership. But here's where it gets controversial. Can their approach truly overcome the massive hardware demands that have long held back fault-tolerant quantum computing? Oxford Ionics, a leader in trapped ion quantum computing technology, has joined forces with Iceberg Quantum, a company specializing in quantum architecture, and particularly in quantum low-density parity-check, qLDPC codes. This collaboration is part of Oxford Ionics' involvement in Stage A of DARPA's Quantum Benchmarking Initiative, QBI, a program designed to push the boundaries of quantum error correction and benchmarking. Their shared mission is to design a fault-tolerant quantum architecture that significantly reduces the hardware overhead typically required by traditional quantum error correction methods. To understand why this partnership is so promising, it helps to know the problem with conventional quantum error correction, QEC, codes like surface codes. These codes are effective at protecting quantum information, but demand a very high ratio of physical qubits to logical qubits, sometimes hundreds or thousands of physical qubits for just one logical qubit. This makes scaling up quantum computers extremely challenging and expensive. Enter qLDPC codes. These codes are gaining attention because they offer robust error protection, while drastically cutting down the number of physical qubits needed. Their secret lies in their sparse and non-local structure, which allows for fast, parallel decoding processes. This means quantum computers can correct errors more efficiently and with fewer resources. What makes trapped ion hardware, like that developed by Oxford Ionics, particularly well-suited for qLDPC codes, is its ability to support long-range connectivity between qubits. Unlike other quantum systems where qubits interact mostly with their immediate neighbors, Trapped ion systems can perform operations between qubits that are physically far apart. This capability, combined with their long coherence times and high gate fidelities, makes them ideal for implementing the complex, non-local interactions that qLDPC codes require. Iceberg Quantum brings deep expertise in designing qLDPC-based quantum architectures and has made significant strides in developing methods to perform universal logic gates within these codes. Their work complements Oxford Ionics' hardware strengths perfectly, creating a synergy that could accelerate the path toward scalable, fault-tolerant quantum computers. The goal of this partnership is not just theoretical advancement, but practical application. By integrating Oxford Ionics' cutting-edge trapped ion technology with Iceberg Quantum's innovative qLDPC codes, they aim to translate current research breakthroughs into quantum products that are commercially viable. This means building quantum machines that can handle real-world problems with fewer qubits, lower error rates, and greater efficiency. Oxford Ionics already reports impressive performance metrics, including low error rates in single-qubit and two-qubit gate fidelities, as well as in quantum state preparation and measurement, SPAM. These achievements provide a strong foundation for the collaboration's ambitious goals. And this is the part most people miss. While many quantum computing efforts focus on increasing qubit counts, this partnership emphasizes smarter, more efficient error correction to make quantum computing practical sooner. But will this approach become the new standard, or will other error correction strategies outpace it? That's a question worth debating. For those interested in diving deeper, the full announcement is available on Oxford Ionics' website. What do you think? Is the combination of trapped ion hardware and qLDPC codes the breakthrough quantum computing needs? Or are there hidden challenges that could slow progress? Share your thoughts and join the conversation.